Computer audio will do. Looks like I'm up and running. Get full screen here. Make sure that the video is pinned to a good place on the board. We can start here. This is a video on completing the cube, the geometric implications of evening off the sides of a cubic, and the graphical significance, points of inflection, etc. So I would put some things on the board, and let's see if I can make sure the whole board is captured. Yeah. All right. So typical problem at the pre-cal and algebra 2 level, putting a cubic and graphing in factored form, writing it as a product. I wish we would say that instead of factoring, taking sums and differences and writing them as products seems to give a better idea of what factoring means than using the word factoring. But these are factors of the volume of this geometric shape. So x minus 2, x minus 10, length, width, height, that kind of concept. And, but looking at it from a graphical perspective, we have y equals x, we have y equals x minus 2, we have y equals x minus 10, three linear functions. And we're going to multiply. And what does that mean, to multiply? Well, let me get a marker here. Let's hope this baby works. Looks good, probably the one I was using before. Well, if I extend these, I probably should have done that before. We have a negative and a negative and a negative. A negative times a negative times a negative means that we have some kind of negative result here. Okay, so let me get that. Some kind of negative result. When this linear function is 0, the function equals 0. And then we have a positive times a negative times a negative. Let's get rid of this thing down here now. I kind of was going to use it, but I'll use this instead. So if we draw a dotted line here and we pick this x value as an input, if we assume that number, we know that's a 2, so a number between 0 and 2 gets us a positive outcome for this one, a negative for that one, a negative for that one. We can see that we have a positive outcome. And again, when we hit 2, we have a 0. And we can continue this analysis, and we're going to get a cubic, and with roots at 0, 2, and 10. And that's important information, when this thing equals 0, to get quick graphical sense. But it's not really, I don't think, the important topic to discuss, which is what we're going to try to do here, or what I'm going to try to put forth here. We can definitely see that there's a point of symmetry here, where I wouldn't call it symmetry, but it certainly is a point from which a numerical pattern emanates. A little bit of a sign change, but we can see max and min's equidistant from this point. And so therefore, there's something interesting going on here, which means there's something interesting going on here. And that's what we want to explore. So let's look at just one of these linear components. And let's, instead of saying mx plus b, let's say ax plus b, which I wish we would change every textbook to. It builds into the other polynomials nicely. So looking at the root, when does it equal 0? And we get minus b over a, which means we really have 3 minus b over a's. Not quite sure how to talk about this at this juncture, but I'm considering how to, and hopefully we'll work out some better explanation as to what's going on. But building off of the quadratic, looking at ax squared plus bx and looking at those roots, minus b over a and 0, and doing that multiplication, we can see that minus b over 2a is the most important x value here, which gives us a minimum. Minimum provided a is positive, of course. And we can see that this root, minus b over a and 0, if we take the average of that root, we've got the x value of the vertex, which is where the numerical pattern of this emanates from, which allows us to put it in a graphing form. Now, from a standpoint, I guess we can see this. Geometry, if you had a quadratic, fancy name for a rectangle, side length of x and side length of x plus 4, and you'd study completing the square. I don't know if you've done it geometrically or not. It's important to do it geometrically. You're evening off the two sides of the rectangle. Multiplying gets us this statement. Subtracting 4 brings us back to the same numerical calculation that is above it. We've evened off the sides, and we call that completing the square. There's good reasons to do it, good graphical reasons to do it, but that's not the purpose of this video. But it does lead us into a situation where we're looking at the area of a square, and it seems like -2 is the key moment. Why? Because any other number you put in besides -2 gets us a positive outcome in that calculation, which means that if we look here and we just draw a tangent, then the slope of that tangent is 0. And why is it 0? Because the y values, as we approach -2 and we square -2 plus 2, they're not changing much. They're changing least quickly at that instant. Everything else is changing faster, right? Faster negatively, faster positively, and increasingly so as we move away from -2 as an x value, right? And so the geometric implications are that writing a rectangle in the square vernacular allows us to see the vertex. Why? Because this is the smallest area you can have in a square. So it's a minimum. Everything else goes up. Unless you got a minus sign or an a term that's negative, then everything goes down from there. All right. So what was significant? Minus b over 2a. Well, going to the cubic. Let's push this up here. Let's take the computer with me. And let's just start looking at the cubic a little bit. Make some inferences. Well, okay, here's a perfect cube. X, X, X. Right? We got X, X. Oh, God, I don't my art skills. X, X, X. Perfect cube, which is a terrible drawing, but we're going to go with it. So some very friendly numbers here. And we can see that the average rate of change from -3 to -2 is 19. The average rate of change from -2 to -1 is 7. The average rate of change from -1 to 1 unit. Then we go in the reverse direction. So our rates of change are being somewhat explored here. All right, as in going up more quickly here, then here, then here, then it's 0, then here, then here, then here. Okay, a picture's worth 1,000 words, so hopefully just drawing those little tangents to the curve give us a sense of the change in the y values in certain areas of the graph. And I'm not sure why I did this, but I think I'm going to analyze y equals x. That's what we started with, I believe, x minus 10. And so let's say that this is 0. Let's draw another one here. That's 2 and that's 10. And we multiply those three things together. You know, what is it going to look like? It's going to look like this graph over here. I kind of lost my train of thought, but we've got roots at 0. We got roots at 2. We got roots at 10. And we're going to boom way down and come back up over here. And we got that signature kind of cubic look. And finding the local max and the local min can be done. You can look at the video on putting cubics in graphing form. It's rather lengthy. It's almost a half an hour. But if you want to dive into what's really going on, got to do that kind of work. So I multiplied this out. X cubed minus 12x squared plus 20x is the factored form multiplied out. All right. And so now we're turning our attention over here. Again, we want to consider minus b over 3a. We saw why minus b over 2a was so important in the cubic, in the quadratic, excuse me. So now we're looking at, you know, the roots 0, 2, and 10. The average of those is 4. And here we have the 0, the 2, and the 10. And here we have 4, which seems to be dang smack in the middle of that drawing. And in fact, there's a reason why. Because if we take that average, then we have actually begun to complete the cube. We've taken the longest side, which actually is x, and we've taken the smallest side, which is x minus 10, and we've taken the smaller sides and made them a little bit bigger, and we've evened off the sides, and we begin to put something in graphing form, which I'll try to do for you here. Again, go to the video on putting cubics in graphing form, take more time with it. The a term remember, we're trying to put this x squared, what was it, x squared, x cubed, excuse me, I'm so used to doing quadratics, x cubed minus 12x squared plus 20x. And we're reshaping it. We got x minus 4, we got an x minus 4. If you put in 4 here, you get these terms here. Notice the 3-to-1 ratio. And if you add up those numbers, you get minus 48. So that is actually the point of inflection now is 4 comma minus 48 is what we just found. C minus 3AH squared is the rate of change at this instant, which is minus 28. And so if you, let me get rid of that because you don't really need it, but if you multiply this out, then you get this. But this is all about rates of change. All right, so we want to look at this written in this form because we get a lot of wonderful pre-calculus concepts to explore. From a geometric standpoint, we know that x minus 4 cubed now is changing least quickly at x equals 4. And we just looked at table values that prove that, all right? And this is a constant. This is the number negative 48. So if you see that change, and maybe I should give you my email address or something. We have some help for you. Yeah, if you see this number change, and we'll take care of you. All right, just everything will be okay. So it's not changing. Okay, but the linear function has a constant rate of change. Hopefully you've had those conversations in class. It's always going down at minus 28 to 1. And again, that's not changing. So we're really looking at, that was terrible. We're really looking at the interplay of the cubic at 4, where it's not changing. The linear component's going down at 28 to 1. And so what's the graph going to have for table values? Something like that. It's going to take on this cubic. It's going to take on that rate of change at its point of inflection. All right, so that's what's going on there. And I just plugged in 4 to make sure that, 4 here gets you 0, 4 here gets you 0, you get minus 48. Going back to the original, putting in the 4 times 2 times negative 6. Just a quick check to make sure I didn't make it careless here, because I tend to do that on the fly here with these videos. So there's 6 types of cubics. There's with a term being positive. When the a term is positive, you have 3 possibilities. You've got one where the slope at the point of inflection is positive, one where the slope is 0, and one where it's negative. Okay, and the counterparts when a is negative, the counterparts occur as well. And taking a quick look at some of these table values here for x cubed, we can see that the volumes, it's hard to describe volume in a negative term, but magnitude maybe. Y values are going up, then they go up least quickly at 0. What happens at 0? That's the no volume moment. And then they start to go up more quickly again. And we get this process. Y values are going up, but less quickly, less quickly, less quickly. Then they cease to go up, and then they start going up more quickly again. Right? And the negative, the reverse. Y values are coming down, coming down, coming down till we hit no volume, which occurs when x is 0. And then they go down faster and faster and faster. And adding a linear component to that changes the rate at that instant. Okay, so as far as I'm concerned, that's more important than Descartes' rule of signs. It's good algebra to practice putting cubics in factored form because it finds the roots. It's important information. I'm not saying it isn't, but I think considering the concepts of rates of change is a real important pre-calculus concept. Half of calculus is about finding rates of change of the calculations at an instant. Well, that basically gets us started on that. And it gives us that instant when you've completed the cube, which means you've taken that calculation and reconfigured it geometrically so that you can see what's going on at that perfect cube moment. That is extremely important. So I think I talked about this. Don't need to talk about that. We did catch that. And yes, let's see if I can get this just briefly, wrap this up. This process does occur. I used to work with Maple, and then they went up to so many different levels, and I lost track of it. So I used to have these in graphing form next to the 4th, 5th, 6th, 7th, etc. I don't think you can use that information. It gets too hard to kind of visualize what's going on. Graphing forms, kick out that second term. So if I was to put x to the 7th in graphing form, we eliminate the x to the 6th term. But trying to visualize a 7th degree, 5th degree, 4th degree, and then what the graph's going to look like gets a little difficult, to say the least. But not with the cubic. Not with the cubic. You can get it down to 3 terms. And if you're considering the rates of change of those 3 terms, for instance, here's 3 terms. Here's a constant term. Here's a cubic that looks like that. And then you've got a linear component that looks like that. So what would happen if you put those 3 graphs together? What might that look like? Well, we got an x cubed. I put it right through the origin. We got something going up at maybe 4 to 1. And we got a constant that's negative minus 20. You can envision this. You can envision this. You can start to look at graphing backwards. So you got negative 20 as a y-intercept. You're going up at 4 to 1 right there. But what's happening? The cubic is making it go up faster. Oh my God. So I almost, that's what that's going to look like. It does have a little bit of concave down, concave up situation right there, but that's what that graph's going to look like. All right. And you can envision it because the rate of change of this, 0, the rate of change of the cubic at 0 is 0, and the rate of change of the linear function is always going up at 4 to 1. And then this kicks in to make those y values go up even faster. And eventually this takes over in a big way as you move away from 0. Okay, so I think that is hopefully what I wanted to say. And hope I didn't make too many mistakes along the way. Look at some of the other videos I've done in haste. And I usually say something, I go, why did I say that? All right, so hopefully this might help somebody.